And so I would like to finish my series of lectures with applications because as it's very appropriate for the WPI, we want to do highly fundamental research, but at the same time, we think about some technological utility that this new fundamental research can enable so that it can improve the quality of life and allow in future more things to be done, including ones that would be impossible without such fundamental research breakthroughs. And our school was focused on themes related to chirality and topology, and I would like to provide today two examples of how chirality and topology enabled objects in liquid crystals, polymers, and elastomers in particular can find technological utility. So there will be two parts of it. The first part will be focused on haptics, where we can use topological solitons to allow for controlling topography of surfaces in a way that one day may be used for very new type of interaction of humans with computers through touch, right? So we know that most of the displays we use connecting us with the world of computers through vision and hearing mostly, right? So this is how we learn, how we listen over Zoom to lectures as an example. But haptic displays are actually also something that's being pursued these days because you can appreciate some people are blind or deaf, and then they cannot hear or see, and yet they can sense things through touch. And so for this type of needs, haptics, I think, are making great progress in terms of being able to convey information. But the future will bring a lot more in this direction where, we will be able to send touches, to our friends, on the other side of the globe. Maybe, all kinds of new experiences can be provided that way. And there is a lot of future potential, but it's not so easy to convey something from computer-generated signals as normally you would have when you have some form of a display to some changes of mechanical shapes and surface topographies that could be then sensed by our fingers, for example. So I will tell you today how not solitons can be utilized for this particular purpose. So this will be first part of my talk, and then in the second part, I'll discuss with you how optical engineering can benefit from knotted vortices as well. Well, we discussed over this school period that topology involves not only surfaces, as in the most commonly known example, where we have genus or Euler characteristic as topological invariance, but also different types of field configurations that can be topologically non-trivial, like singular point defects in here and solitons like skyrmions. And they can be very well understood and classified. And I remind you that yesterday we had a fantastic tutorial lecture by Munetto Nita that discussed the classification of these objects with the help of homotopy theory, right? So, and in here you have singular defects that, elements of the first homotopy group of Phi1 of S1 spheres, and point defects that are elements of that second homotopy group. So This topology in here refers to singular field configurations, but we also have it in topological and non-trivial solitonic field configurations. And again, yesterday's tutorial very nicely classified them, including skyrmions in particle and nuclear physics, in condensed matter systems, like magnets and liquid crystals. So you have now this, I believe, I hope, solid background of such topological non-trivial field configurations. Some of them are themselves like Hopfian's knots and non-singular field configurations. Some of them are vortices that can be used to form knots, and I will show some examples how that can be done and utilized even in practical applications. But importantly, these field configurations are somewhat different solitons than, another common example, like solitons in waters, on surfaces of water that were originally discovered on a channel in Scotland. Such field configurations, as we have seen, can be of solitonic type and singular type, and they can coexist with each other. So, for example, in here are solitons, domain walls, and skyrmions in liquid crystals that have order parameter spaces like S2 mod Z2 or S2, depending on whether we have polar or non-polar type of liquid crystal. And so now we can combine them together to form hybrid structures that we called torons, right? So because we noticed already in this overview, including monetonitas yesterday and what I briefly showed you a minute ago, both the point defects and the skyrmionic tubes are elements of the second homotopy group of spheres. So at the level of mathematical description, they are the same objects. At the level of physics, they are quite different from each other. And what's interesting is that we can form hybrid structures that we call torons, where a skyrmion tube can terminate on point defects, right, of the same homotopy class with the same Z integer number that describes how many times such field configuration wraps the order parameter space as you do some mapping. And then these topological solitons, torons that we form in this case, right, have singular point defects and non-singular skyrmionic structures that for every single point on the order parameter space S2 have these peculiar preimages that have chiral pattern to them, as you can see visualized in here, and kind of vividly showing us that they are stabilized in a chiral liquid crystal medium. And so now such torons can be realized in different types of systems. What I will show you today is how we realize them in polymers and elastomers. And with that, we can use topology to control topography. But before I do that, I just want to remind you what are rubbers, right? So polymers. Polymers are everywhere around us. Most of the things around us, our clothes, is polymers of different kinds, right? With different degrees of polymerization, smaller or longer molecules give us very different properties, even if chemistry is, chemical composition is similar. The length of molecules typically defines properties that can differ quite a bit, making them solids or liquids and so on. And so one type of polymeric system that's particularly interesting are so-called rubbers. They have molecules that are weakly cross-linked. And that weak cross-linking is very important because when we have such polymer chains, they can exploit different conformational states under the effect of thermal fluctuation, say at room temperature. So, for example, if you look at this little chain in here, it is not fixed in space. It will thermally exploit different configurations. And because of that, the entropy can be maximized. And because of that, the rubbers have very interesting properties of the so-called entropic elasticity. How many of you heard about it? Entropic elasticity, right? What does it mean? An entropic elasticity, as you heat rubber, it becomes stiffer, very different from, you know, say, common solids, like glass, for example, right? So this is because as you heat the system, these conformational changes can, you know, more easily go from one state to the other under the effect of thermal fluctuations. And so now what we can do is we can polymerize these rubbers from liquid crystalline states where the molecules that are monomeric units that can be bound to each other because of the you know, presence of photoinitiator that promotes cross-linking, then you know, we can start from a fluid nematic liquid crystal, conventional type that I was, you know, overviewing in my first tutorial. And then as we shine light and excite that photoinitiator, we promote cross-linking and we convert it into solid. But with that, we can preserve liquid crystalline order. And when a rubber is liquid crystalline in nature, it will have much richer properties than rubbers we use, for example, in tires of our cars or bicycles or in shoes, in clothes, you know. So we'll have different properties. And the one of them is that the response to external stimuli will be highly dependent on orientation of this director, the average orientation of monomeric units that form this rubber. Now, moreover, what's important is that we can cross-link this rubber locally. And you can see in here that even a femtosecond laser source can be used to cross-link in diffraction-limited spots of the material. So literally, I can take this tight sapphire laser beam and focus it to tiny volume, and then cross-link my rubber, converting it from liquid to solid locally. As I do so, I freeze this material locally, and it becomes solid. And then I have the power of steering the laser beam, so I can make all kinds of particles. For example, the little donut-shaped particles you can see in here. And then these donut-shaped particles can respond to external stimuli in a highly you know, interesting way. So you can see these particles would shrink or expand in different directions as you heat them and cool them, right? So for example, this donut is becoming elongated in one direction, which is perpendicular to far-field director, the average orientation of liquid crystalline molecular ordering, and shrink in the other direction. And with that, we can choose conditions to be right to open and close the hole inside. So with that, we can change topology of these colloidal particles, going from genus 1 torus to you know, an object without a hole that is homeomorphic to sphere, because you know, this process allows us to anisotropically shrink and expand such objects. So you can see this done in here, you know, for such objects, and you know, some more examples of such control where we can, at low and high temperatures, control topology of these objects. As we would, so in here, the heating was done uniformly everywhere, where these colloidal particles are dispersed. But, and as you open and close these, holes in different way for different types of particles polymerized at different temperatures. But we can also scan the laser beam and heat it locally. And with that, for example, a rod-like elastomeric particle can be shaped into any arbitrary shape you wish, right? Including examples you can see in here, but there are many more. So, not only this rubber, unlike the rubber we have in, tires of our cars, is highly responsive in an isotropic way, but it can be also actuated locally. And with that, we can control shape in unprecedented way. And including not just shape, but also topology, change in genus, for example. Well, but this was something that involved topology of surfaces, right? Or, just shape, geometric shape of particles. Now, as I promised, I would like to demonstrate an example of how topological solitons can be put at work, right, or nodes in the fields. And interestingly, there is a very popular web-based series, seminar series called Solitons at Work. And so in here, in there, I think the name of that seminar series program, as organizers sometimes admit, is kind of a dream, futuristic dream. But I'm hoping that today I will show indeed how solitons at work can mediate, the topographic changes of surfaces of materials. And so in this case, as I showed from the very beginning, we have a collaboration with, that's very slow. With our colleagues at University of Eindhoven, so Dick Broer, Danchink Liu, and two of the students, Jacques and Darian, were involved from my group. Darian was actually an undergraduate student when he was doing this research. And so now the group of Danchin Liu and Dick Broer provided us with these chemical compounds that could be then polymerized when we form these topological solitons. And so let me now show you what capabilities this allows us to have. So here we have many such solitons I described to you that we called torons, right? The skyrmionic tubes that terminate on point defects. In magnetism, they would be referred as Bloch points. And so now what I will show next is that we can exploit this topology to control surface topography to go from that of an array of holes, like in this case, to an array of mountains. Imagine you can do that in, at the larger scales, right? Convert the mountains into valleys and back, well, on the scale of material surfaces, we can do this, and we can do this with temperature or light. So both being external stimuli. And actually, this video in here shows you, the mapping of the surface topography that is changing as we shine light, right, in response to optical excitation. So the materials that were provided by the group of Danchin Liu and Dick Broer are shown on here. These are the chemical compounds that we used, including the photoinitiator and also the chiral additive that you can see in there. And now, as you know, I promised, we can change the surface topography to go from that of holes to that of the mountains, or invert the topography, as you can see in here. So what we do in this case is we start from a liquid crystal cell in which we have this initially fluid liquid crystal that is composed of all of these compounds in it that are cross-linked with each other upon, that are not originally cross-linked with each other, but just mixed, right? And then that chiral liquid crystal that's formed in the process of mixing is then confined between two substrates where we define perpendicular boundary conditions on these two surfaces. And then as we polymerize it at certain temperature, say 40 degrees Celsius, as we heat to higher temperatures, we will have the mountain-like topography. And as we, cool down, we will have the hole-like topography as depicted in here. Sometimes this is not working, but let me try again. Okay, and so as you can see in here, that by changing temperature, this topography with this parameter in here, given some relative height, can be controlled continuously. Okay, so I mentioned to you before that the objects that enable this are the torrents, and the way to form them in liquid crystals requires meticulous control of surface boundary conditions, because for weak boundary conditions, we would have a Skermian tube. And then for stronger boundary conditions, we can have these point defects that would be then terminated at these points, right, analogs of the block points in magnetism. We can understand the stability of these torrents by minimizing from causing free energy, and here with the chiral term, here in the second term of the free energy functional, with additional surface interaction terms describing anchoring properties of liquid crystals. And then we can map the regions of stabilities. And of course, as I already mentioned, the one of interest for us for this application are the torrents. And so we find that they are stable in this range. Then we form them and we can image them. So we can reconstruct them from numerical modeling that utilizes minimization of free energy and gives us this type of field configurations that can be then visualized with the help of pre-images in the form like you see in here, where for every point on the surface of the order parameter space, we have a region that connects two point defects, block points, and has this chiral configuration. And now, as we can see, we can image this topological solitons with the help of nonlinear optical imaging, which is based on 3-photon absorption of the molecules of liquid crystals themselves that then emit as we excite them in infrared, emit invisible because of third-order nonlinear optical process of absorption, and then subsequent emission. And then as we obtain different cross-sections in the plane perpendicular to far-field director and containing far-field director, we can see good agreement between the experiments and these simulated results. And also we can find, conditions under which Skermians are stable too. And actually both can be utilized to control topography in different ways. So in here, they are again visualized in a different way where the orientations are vectorized and correlated with the order parameter space. And so as we would then also construct the Pontiac-Sum construction which, pretty much embodies pre-images for a given polar angle. We can see this kind of pattern for them, right? So again, reminding you that this is just a superposition of pre-images. And so then for torrents, we would have this kind of use of pre-images that are shown in here. And indeed, we reconstruct them from experiments and find being consistent with the results of modeling. And then here you can see visualizations of such torrent structures in experimental and computer simulated field configurations. So now it's important to understand that the structures of torrents and skirmins and liquid crystals can emerge in different locations as we quench the material from isotropic state. And they can crystallize, but we can also use laser tweezers to define the locations of such topological solitons. So in fact, in here you can see an example of how an array of such topological objects can be formed with crystalline ordering that also has 5-7 defect in this lattice that can be used as an example to generate vortices in light. So phase singularity in light that you can see in here, and also in a diffraction pattern from this type of diffraction grating, where for every single first order beam, you can see a hole which is a bit small, right? Because these are the elementary charge vortices. And then in the second order, you see bigger holes, and these are already the Q equal 2 charge vortices and so on. Now, importantly, so in this example in here shows just phase profile for one of these optical vortices generated this way. But what we were interested in was to control these torrents in such polymerizable material so that we can then control the surface topography at will. And so, well, we started from defining the logos of universities. So CU and TUE, and perhaps SKCM² should be added for the next time. And so the collaboration started before we had the institute, in fact. So, however, you can see in here now, so how did we define these soliton locations? With a laser tweezer, we can melt liquid crystal locally, and then it will transition to, have such topological soliton in the place of melting, right? It's important to understand that topological solitons are protected by topology. They cannot appear in any place, effortlessly, but we can, rather than quenching the entire sample, and then in that case, they appear everywhere, right, spontaneously, we can heat and quench locally in whichever place we shine the laser beam, and then we have them in well-defined positions. Moreover, at some laser power, we can pin their location so that Brownian motion will not diffuse them away. And then after this, we can, shine a light appropriate for the photoinitiator at, some UV wavelengths, say 380 nanometers. Then we can cross-link such sample. And then as we would polymerize it, in this case at 50 degrees Celsius, right? That film within which we have these solitons is flat. The color in here is showing surface topography. But now, interestingly, as we cool it down to room temperature, we got the array of holes that, reproduces the topology we have within it. So for every single toron, we have a hole, right, in that place. And then as we heat it to high temperature, you got protrusion at the surface, a little mountain, right? And again, as we change temperature, this can change continuously. So, well, you could say this is just temperature. You will not want some haptic device to be heated, 250 degrees. That would burn our fingers, right? Yeah, this is not what we intend to use for applications, but remember, liquid crystals respond to all kinds of stimuli, electric fields, and light as well. And so I will later show how light can control topography, but electric field too could. And, in our displays, for example, we utilize response of conventional fluid liquid crystal to electric voltage of only 1 or several volts, right? So, okay, well, this is just a demonstration of the capability, right? But now an important part was also to somehow do numerical modeling that would capture this power of our topologically non-trivial liquid crystal elastomer system, right? So in this case, what's important to understand is the basic principle of the response of this medium to external stimuli like temperature or light. So the important thing is that when the director is in a certain direction, when we increase disorder, then the material will tend to shrink along the direction of director and then expand in the direction perpendicular. And you can easily understand it by just imagining rods, right, which point in a certain direction. And then as you disorder them more, they will point more to the directions orthogonal to that original direction. So when the molecules are cross-linked, that results in contraction along the director and expansion in directions perpendicular to liquid crystal director. And that can be easily captured by some coefficients of expansion at different temperature, which are large because we can have 300 strain just by changing temperatures. You could see the response was very dramatic. And so now, as we numerically minimize the free energy of the liquid crystal, we can get energy minimizing director field configuration that we have before polymerizing it. Then we cross-link, we freeze it, and then we change temperature and it actuates. So we have the director structure from minimization, and then we can, apply this response in here, right, in terms of expansion coefficient. And then, with that, we can model the height contribution, actuation of the height of the sample. So indeed, we can reproduce the behavior. So you can see in here, experiment and modeling, they agree quite well. There are some tiny details that are just referring to resolution of the system, right? Because also being able to image that profile is not infinitely, perfect resolution that we have in experiment, right? But it's very consistent. You can see not only we capture the fact that, at high temperature, in the place of presence of this topological soliton, we get a mountain, but there is also a little deep at the top of it. And again, we can capture this behavior quite well in experiment. But there are many different types of solitons that, go a little bit beyond just torons and skyrmions and hopions, right? Where the solitons can bind together and, if we think about solitons as analogs of atoms, then they can form analogs of molecules or even macromolecules or polymers themselves. And so here we thought it would be kind of interesting to give such an example where we also realize solitonic analogs of macromolecules. So, in other words, a skyrmion is atom or even a nucleus, right? Then, as we create a toron, we could think about it as becoming an atom, right? Because you could think about the 2-point defects becoming analogs of electrons, perhaps, and then we can then bind such objects with additional analogs of electrons, which would be these point defects, right? And so then you can see we form molecules and macromolecules. And an example, the simplest example of like diatomic molecule analog is the so-called twistion that we, discovered experimentally, that has overall 6 point defects. So 2 for each toron and then 2 binding in between, right? It's an analogy of, the covalent bonds formation in conventional atomic molecular systems. And so now such a topological soliton molecule can be again actuated as we change temperature after polymerization, so also macromolecules like this. And you can see again, we can go from these valleys that have level lower than flat surface around to the mountains, right? But the very interesting features, that you can see in here emerge from combining multiple topological solitons into solitonic molecular analogs. And, again, in here you can see these experimental results that illustrate such actuation. Well, and so then, remember, we also had Hopfians, right, discussed within this school in light, in liquid crystals, and magnets in different systems. And so I'm just showing this slide. It was already part of my tutorial lecture as a reminder. These are the type of topological solitons that have the linking number or Hopf index of the topological invariant, the elements of the third homotopic group of spheres, and the integer numbers in this case correspond to linking numbers. Also, the number of times that the hypersphere can be wrapped around the S2 sphere. So now we can realize such objects in liquid crystals. And again, I already discussed with you these solitons, right, that can be realized, imaged in experiments with pre-images visualized and confirmed. And again, as a reminder, I'm showing you the composition of pre-images as they fill the three-dimensional space. Now, it crossed our mind that such objects should be also very interesting from the standpoint of view of actuating surfaces and changing topography in response to stimuli, right? So here you can see this movie showing all the pre-images. The pre-images are regions where the director points in exactly the same direction, right? And they have the shape of closed loops or topological circles, right, that correspond to every single orientation. Well, but now you remember that the peculiar property of these liquid crystal elastomers is that they would shrink along the director for every single this orientation direction and expand in direction perpendicular to it, right? So now the question is how this beautiful topology in a material with that property of expansion and contraction for all of these different pre-images corresponding to order parameter values would, give us some interesting functionality. So again, in here you can see the surface actuation of such topological objects, and this behavior is reproduced in our modeling. you can see that in this case, the peculiar nature is that there are, you know, well, in some way, to me, it was reminding some of these fountains, you know, that you sometimes see in cities, downtowns of cities, right, where, you know, the water can form such peculiar shapes that then can be controlled how exactly they evolve. And this is, you know, something we do experimentally and see in numerics, where, you know, with change in temperature, we can go from these double circular valleys to double circular mountains as temperature is controlled. Yet another example of soliton that I would like to show, which is purely non-singular, but and it has closed loop preimages, but they are not linked. So Hopf index in this case would be 0, but such solitonic structures are stabilized purely by chirality of the system because they embed twist locally. And so again, for this configuration where you can see preimages, you know, that are tiled together into Pontiac and Somme constructions that are viewed from two different perspectives, we can see that, again, upon change in temperature, we can control very peculiar features of topography. And then again, these experimental results and computer simulated results are highly consistent with each other. You can see that this behavior, this response is very strong, and therefore it is interesting from the standpoint of view of haptics applications, because every single you know point with such an object can be potentially used as a pixel of a haptic display that will control your sensation of touching the surface, right? And so in this case, it was done with temperature and light, but as I mentioned before, we can also control them with electric fields. So yet another example of solitons we discussed before were these helinotons, right, that have the dual nature of Hopf solitons and also vortices and non-singular lambda lines formed in Kaitau fields. I will not remind you, I hope you remember from previous lectures, details of these types of configurations. But again, we can polymerize them and we can see these interesting responses in liquid crystal elastomers and polymers that allow us actuating surfaces. And in this case, you can see reproducing some features that have multiple peaks, you know, different from the ones we had before for torons, twistions, and some analogs of solitonic macromolecules as well. This is the first half of my talk, and I think I am, I'm gonna to maybe accelerate in the second part. But in here, I gave you examples of how topological solitons in liquid crystal polymers and elastomers can be used for controlling topography of surfaces, right? And this is mostly what I showed, done on a single pixel level or demonstration. You can tile them into different configurations and have them effectively pixels of haptic displays. But engineering can push this much further, right? So by, you know, engineering chemistry of the molecules and responses and the ways of patterning and so on, displays, haptic displays can be made that could allow us to, you know, experience, you know, the things and send some, communicate with each other remotely through touch as well. So maybe I can stop here and answer questions to this part, if there are, and then we can continue with the optic, part of my presentation.
Thank you. And here the thing about how after the break. Now if you have question, please.
Maybe we don't need a break, just the
break.
question break, just questions.
Just question, yeah.
Yeah, but because the second half will be shorter, and then 3 p.m. is not far, but we need to have coffee, tea time.
Yeah.
And there is also some activity for students, yeah.
I see. Anyway, if have a question, please. Yeah, please, Shinsuke. Please use.
Thank you for the nice talk. I have a question on the experiment technique. When you generate a torrent in the pneumatic sample, you locally heat the pneumatic region, and the liquid crystal order is disordered and melted. I'd like to know about the role of the size of the lasing spot, because when the melted region is too small than the Hecker pitch, the liquid crystal phase cannot twist spontaneously, I think.
You're very correct. So, typically, the laser tweezer lets you do that melting on the micrometer scales, right? And then that's typically sufficient for you, or larger, right? You can make it as large as you want. So with that, you can have resolution good enough to generate them at will in desired location, right? Indeed, if you would have very large pitch and try to heat it locally at a spot that's much smaller, this may not help, right, to generate them, but one can control these scales appropriately. And if your heating spot is larger than, 1 torron, right, you could generate 2 or 3 at once, right, in this bigger area. So if say you want to increase the throughput, then you could control, your strategies of how you do it as well. There is also another aspect, depending on how you tune the confinement pitch and thickness of the sample. In some cases, you don't even need to melt it, right? Because typically, if you can generate singular defect, that can also mediate creation of a torron that then, could be generated through realignment, like optical Friedrichs transition type of realignment as well.
Oh, thank you for the answer. This question is I have the question since I've read your paper. Yes, my question is totally solved. Thank you very much.
Thank you.
The other question? No, I have.
Okay.
If you make melting by laser with electric field, how happen? Positive field is easy, maybe. You sand it by transparent electrode, and then you apply the electric field this way or that way to make a torron.
Yeah,
What happens?
it is possible, to do like this as well. The only thing is you need to pattern electrode. It's exactly what we do in displays in principle.
Yeah.
There is no complication with that. In principle, it is much faster to do with laser beam because you can steer it and create any, like you can literally somewhere else. I could show you, my students were drawing cats with the torrents, not just something simple like a logo or whatever. There is a lot of power, and if for every single pattern you will want to create patterned ITO electrodes, that's more work, but it's doable, of course.
Okay, thank you. Yeah.
One idea, one comment is here you are patterning the surface with laser.
Mhm.
And did you think, for example, that maybe with holography you can pattern the bulk in your material? It should be possible.
Yeah. It's a
by
good
playing
question.
with
So
several
in
lasers.
this one, I will start discussing.
Ah,
In the previous one, the surface was trivial. It just was perpendicular boundary condition. And then the light was just melting. In here, indeed, I will discuss how we can define the structure and topology of this liquid crystal field configurations through the response of such azobenzene dye molecules that are grafted on surfaces. And you're very correct that very similar azobenzene dye molecules can be dissolved in liquid crystal, and then you can control their conformations in the bulk. And with that, you can induce transitions between disordered and ordered states or change pitch or chirality. You can actually invert, because there can be molecules that will allow you to invert the handedness, go from left-handed to right-handed. So, for example, molecular motors that were recognized by Nobel Prize by Feringa also can be used as chiral additives for this type of liquid crystalline materials, right? And they can be in the bulk. And when they are in the bulk, you can change the pitch and, very interesting, lots of, potential fundamental science and applications.
thank you.
If you have a short question, we can accept one. If not, do you continue?
Yes,
Okay,
continue.
then let's go to the second part.
All right. Well, so now I would like to discuss with you how we can create singular vortices, including when we make them form knots of different kind, and with that control light, right? So first, we actually use light to control liquid crystal. Then we will use liquid crystal to control light. But to control liquid crystal first, to take some well-defined patterns with topological objects like vortices. On the surfaces, we graft azobenzene dye molecules that have this type of chemical structure you can see in here. So you can see that these groups in here allow you to graft such molecules on the glass surface very easily. And then as we fill in liquid crystal, as we shine laser beam, not just laser beam, but any light which is linearly polarized, these moieties of azobenzene will try to orient perpendicular to the laser, to the light polarization direction. And so we can pattern them, into structures like this, where all the colors depict the regions where the moieties, have some orientation, right? And then as we fill in liquid crystal, the liquid crystal molecules at surfaces orient parallel to these azobenzene moieties. And then with that, we define the topology of field configurations in such media. So for example, we can create an object like you see in here, which is a vortex line that is perpendicular to the screen. And actually, you can see that when we shine the laser beams, these laser beams in this case are optical solitons, which exist in liquid crystal medium because of interplay of nonlinearity of the response of liquid crystals through realignment of optical axis with the that compensates for diffraction of light, right? So they then become self-focusing. And then as we send these beams around such an object, right? So remember yesterday in Moneto's presentation, this was rods falling around. Yeah. So that type of configuration that we have. And then you can see that the numerical predictions that we can make closely agree with the experimental data that are shown here by sending these laser beams of light, right? And they are deflected in different directions around such a topological object. The very interesting thing is that you see here two different lines, red and dashed yellow, that totally overlap on top of each other. So we had to plot them in this way. One is dashed but thick, and another narrow but continuous. And they agree with each other. So one is based on liquid crystal optics. The other one is based on cosmology predictions for interaction of light with an elementary cosmic string. And we plot them on this kind of pattern, on top of this pattern, where, of course, we disregard the actual length scales, right? Because for cosmology, those would be light years. For liquid crystals, those hundreds of microns or millimeters, right? And so now we can pattern different types of vortices. For example, in here, you can see half integer one with this kind of different structure, and you can see how it would deflect light when beams are coming from this side, or the -1/2, this one is +1/2, with different orientations of incoming beams. And in this case, with concentric orientations of director. For all of these, there is a very good agreement with experiments, right? So the modeling of two different kinds very closely captures the experimental behavior. But now I give more examples. So in here is a -1. So these are objects, as you recall, in 2D, right? So you have -1 and -1/2. And again, there is a very close agreement of their behavior for the other different orientations as well. Now, what happens as we increase the value of optical anisotropy by going from very small to large, and the largest we could have in liquid crystals is like 0.8, but you can have even larger if you make metamaterials, right? So then you can engineer something on the order of 3 delta n. So difference between extraordinary and ordinary refractive indices of liquid crystals. So here, I hope you remember some of the tutorial content from Professor Lin, who was discussing the optics of liquid crystals. And you can see that as we send the beams of light into concentric and radial vortex structures, the behavior is different, and the delta n increase of optical anisotropy makes this response much more dramatic, right? And that is consistent between modeling and experiments that gives the same type of behavior. And again, we also can pattern vortices with different winding numbers, so 3, 4, 6, 9, arbitrary. So in this case, as you observe these vortices between cross polarizers, the winding number is correlated between the number of dark and bright brushes you see between cross polarizers. And again, what we note is that the larger is the winding number, the more dramatic response of this medium is to the incoming laser beams, which makes sense because your spatial variation of the optical axis orientation is more dramatic as you increase winding number. But then we say, well, why not making crystals of vortices of this kind and then see how light would interact with them? In the beginning, I mentioned cosmology analogy. Well, this is going beyond cosmology, right? Because while people these days very actively looking at the gravitational wave experiments data, that are attempting to unambiguously verify existence of cosmic strings, right? we do not expect there would be crystals of these cosmic strings somewhere in space. If there would be, that would be extremely interesting because maybe you could travel in time. Well, let's see what we can do when we realize such structures in liquid crystals. So in here, you can see we made crystals out of half integer -1/2 and +1, where for every unit cell, it's important to, and for overall the crystal, it's important to have the neutral overall charge of optical vortices. And what's interesting is that when we pattern an integer strength vortex, as these lines in this three-dimensional bulk tend to split into two half integer ones that correspond to these dark spots in here. And the reason is because the free energy corresponding to these vortices scales quadratically with a winding number. So therefore, an integer strength or winding number vortices is replaced by two half integer ones because they cost twice less energy. Now, as we send these beams, so this, as I remind you, the optical solitons, we can see they can meander within the quasi-atoms that are these topological objects, right, in the lattice. And this can be reproduced very closely in experiment, in the modeling consistent with the experiment, as well as in this case where the different beams would be, sent from different directions and therefore show quite different, very nice behavior. Now, as we would have large birefringence, and large in this case would be on the order of 0.4, right? Then we would have light localized spatially, right? And then the challenge is a little bit that materials with large delta N at this moment are not room temperature material. So in order to do this, you would have to heat the sample because at room temperature would be crystal with, too many extra defects that scatter light, and then that would not also host the optical solitons as in solitonic nature. But when we generate high winding number solitons, like the ones you see in here, then you will see we can actually spatially localize light with materials that are similar to the ones we use in our displays. So no new chemistry needed, just the new types of lattices. In this case, we patterned lattices that have +3 vortices, -1 and -1/2, right? Shown in here in this array. So this is visualization, numerical visualization of the actual structures seen here between cross polarizers. And very interestingly, I went too far. As I will look at these structures in a bright field microscopy without cross polarizers, I'll see that in the center of +3 object, I actually have 6 dark spots. What that corresponds to is, remember, +1 vortex was split into 2 half integer ones to reduce free energy. The +3 is split into 6 half integer ones because that allows it to reduce free energy, right? Dramatically, because 6 to the power 2 is 36, whereas if you split them this way, you reduce it 18 times, right? So then what it means is that in the field configuration, on the large scale, we have everything as we pattern it, but locally, there is additional feature that corresponds to splitting of this core of +3 vortex into 6 half integer ones. And we will see that this effectively creates revolving gates that will control optical solitons in a very interesting way. One of the things that we observe is localization of light. I mentioned to you, this is commercially available material, most widely used liquid crystal, the cheapest one you can buy as well. In it, you can see we localize light into closed loop that interacts with these vortices in a predictable way. And also we can, generate many other patterns of light propagation. Yet another very interesting thing is the fission of the optical solitons with the help of topological vortex lines. So you know that just like atoms can undergo fusion and fission, or nucleons, right? In a similar way, the analogs of atoms or nucleons, the solitons, in this case, optical solitons, can do it too. And so, we can see that when we send the beam in some particular location that correspond to these revolving gates, right? That, you remember, are the vortex lines of +3 that split into 6 half integers, we can, generate dotted solitons. And again, we have very good agreement, and these splittings can happen between experiments and modeling. These splittings can happen multiple times. So you can have dotted, granddaughter type of solitons. But a very simple way to understand this is that the solitonic beam of light is incoming, and when it crosses such a vortex line, you can see in here, part of it will be deflected in one direction, part in the other direction. And then if power is sufficient, these solitons will be remaining as optical solitons. You remember, you need to have some threshold power to distort optical axis in order to create nonlinearity sufficient for their existence. On the other hand, if the power is not sufficient, then they will decay, intensity will decay, and then it will be scattered out, right? And here are some examples of emergent effects. We shine laser beam in the same direction, but as you adjust by micron of 2 or 3, and you cross this vortex line from one side to the other, you can see these dramatic responses of the beam propagation pattern, that result from this behavior. So we can control the light propagation of these solitonic beams by applying external fields. And here I show how angle of deflection can be changed by some 180 degrees or even more as we apply voltages on the order of up to 5 volts. And then we can also use light itself to control the solitonic beams. In this case, we have the surface with azobenzene dye. And if we shine light of particular wavelengths, we can repattern it effectively. And then that can be used to deflect beams in different ways. Now, you can, looking at it, recognize that technological utility, that such effects could have. But very interestingly, these phenomena are closely related to what was discussed many decades ago for still elusive cosmic strings, right? So already from the time of Keeble, who was first one to predict or propose the existence of the cosmic strings and how they would appear right after the Big Bang, many people were thinking how to detect their existence. And of course, one way that they could come up with was using light coming from distant stars or other objects in the universe, and probing interaction of light with these cosmic strings. And so, well, space is vacuum, right, most of the time, and therefore it's boring interaction of light with vacuum, you would say. But nevertheless, you have the curvature in the space-time. And there you have this kind of cone-shaped space-time around each vortex, where around each analog of liquid crystal vortex, which is cosmic string. So just like a small fragment, a meter-long fragment of cosmic string would be heavier than sun. So the mass density is very large. And then you have very strong interaction of light, with these objects. Very strong is kind of relative term. We know that Einstein was able to explain the effective focusing and deflection of beam of light by heavy extraterrestrial objects like sun or quasars in his theory. But when you have vortex lines, right, the cone-shaped geometry of the space-time is well defined, and then you will have such deflection that can be then observed, for example, from the Earth. Now, I plot in here this cone-shaped space-time atop of the structure of defect in liquid crystal. And I mentioned that if you adjust the length scales, the scale bars, they're the same. And in fact, you can map predictions of one theory to another by plotting together, the deflection angles as a function of, in liquid crystal case, delta n over effective extraordinary index, delta n is optical anisotropy, and then some linear mass density that can be plotted in, different units for extraterrestrial objects and cosmic strings. And so you can see that the cosmic strings and liquid crystals show the same behavior. They overlap. It's as you can see. And then only at some large values of delta n that there will be some departure from such, simple behavior that, we will see, as you can see here. Now, if you compare the deflection capabilities of liquid crystals and extraterrestrial objects. So, for example, the strongest steering capabilities in the universe have these quasars in here. They are record-breaking deflectors of light, right? You can see that many liquid crystals with these types of vortices very easily outcompete cosmological objects. But, well, it's good to see for liquid crystal people, I think. But, the cosmic strings, are somewhere here. And while, on one hand, we could use light to probe potential existence of cosmic strings. One challenge is that, such objects like extraterrestrial bodies like stars and quasars also deflect light. And therefore, it wouldn't be unambiguous. Why did it get deflected? What is the source of deflection? Is it some black hole quasar or some, or some cosmic strings, right? This is why now people are additionally using gravitational waves to probe existence. And recently there have been a series of papers actually seeming to confirm, but so still needs to be more broadly accepted by the community, the existence of cosmic strings. And once we have well, once we can pin down their location, we can also use light and you know, kind of correspond that to this you know, detection of cosmic strings and probe also deflections around them. And so, but very importantly, liquid crystals can be used as cosmology in laboratory type of model systems to understand how light interacts with such topological objects. After all, in both cases, the interactions come from Fermat principle, right? Because light always takes the shortest pathway between the different points in space. And again, we can use light in liquid crystals to model such behavior, but then it can provide insights into how we can supplement gravitational wave experiments with optics to probe, you know, existence of cosmic strings, pin down their location, and test various different theories. However, as I described earlier already, the ability of liquid crystal vortex line to deflect beams of light and control their propagation comes from the Fermat principle, right? So pretty much if you have some points, y and y prime, the trajectory of light propagation will be the one that takes shortest amount of time to travel, right? But now in liquid crystal, where we have the effective cone of refractive index, right? That geometry is defined by you know, orientation of optical axis pattern, right? And this is what we minimize. So as we minimize it for different field configurations, we see what refractive indices light could see in different parts of this pattern as it propagated, right? And then that gave the shortest amount of time to get from one point to the other as it propagates. And so again, this is the analogy to that gravitational cone, right, in space-time that we were looking at before, but now defined in terms of liquid crystal optical parameters like refractive index difference, delta n, optical anisotropy, and extraordinary refractive index. And so now having this insight, we can pattern the structure of liquid crystal vortices and then not only localize light into circles, which are unknots, but also localize it into knots. So what I demonstrated to you before was done in 2D, and in 2D you cannot make a knot, only a knot, right? So now, however, as we pattern the vortex lines into knots, you know, that are made out of the two half-integer twist disclinations, then we can localize light into knotted configuration as well. So this was published recently in Nature Materials and Nature Photonics, and some earlier work that did not involve optical solitons, but just you know, conventional diffracting laser beams was published in PRX. Now, however, here I show the knot vortices in liquid crystals that can fuse. And so what we dream about doing next is having light localized into knots that can then fuse. And with that, the beams can recombine. And so you can imagine that we can control fusion and fission of such vortex lines, and he is done already for them, just not yet with confined light. This will be coming next, and knots of arbitrary complexity can be generated. Therefore, you can localize light within these complex knotted patterns, and that might be the next let's say, the future of virtual reality or augmented reality applications that we can think about. So this would be all. Thank you for your attention, and I'm happy to answer questions.